The next type of RC oscillator that we're going to consider is our Wien bridge oscillator. So we can see our basic schematic here, and so a couple things to note about the schematic. We can note that in this case we have a non-inverting configuration. So non-inverting amplifier configuration, and that's because we have sort of our input, which again, I'll make a note explicitly here in a second, has been included just to aid analysis, but we see that's connected to our non-inverting terminal. So that non-inverting amplifier configuration is going to introduce 0-degree phase shift. And so what that means is that if we want our overall phase shift to be 0, we want our feedback network to also introduce 0 phase shift. Feedback network, we want that to be 0 as well. So let me just put here above this arrow, this is what we want. And so the reason for that again is so that our net phase on our loop gain function, so remember our loop gain, which was T of j omega, we want that to be equal to 1 angle n times 360, where our n is equal to 0, 1, 2, and so on. And so we're targeting, again, this case of n equals 0, so we're going for a 0-degree phase shift around that loop. So a couple other things I'll just go ahead and note here while we're down here talking about it. Like I just mentioned, our VI is just included to aid analysis. We don't actually need an input for oscillation to occur. So that's kind of the whole point of oscillation. And another thing that we have assumed before, which we're going to assume here as well, is that any frequency effects of our op-amp are happening at much higher frequencies than our oscillation frequency. So much higher, so we're actually assuming that this is much higher than our corner frequencies for our RC networks. And so we see here we have sort of two RC networks. And in order to aid our analysis, let's go ahead and sort of mark what these are. So right here, we have a RC network, and let's call this total impedance Z sub S of this series network. And so this is actually going to be a high pass network. And so we can see that this is going to be a high pass network because let's consider our capacitor impedance. So remember, our capacitor impedance is 1 over J, or negative J over omega C. And so what we see with that is for large values of frequency, that's essentially going to be 0. So for high frequencies, that's going to be a short for our capacitor, it's going to pass through. But for low frequencies, it's going to be infinite impedance, and it's going to block. For 0 frequency, it's going to be infinite impedance, and it's going to block signals. So our other IC network over here, we see is in parallel. So we're going to call this total impedance Z sub P, and as you might guess, this is going to have the opposite function of that blue network there. This is going to be a low pass network. And we can come back to this definition of our capacitor impedance. If our signal frequency is 0, we're going to have an infinite impedance, so the capacitor is essentially not coming into play. We're going to have voltage dropped across that resistor. However, if our frequency gets high, our capacitor impedance becomes really small, so it's essentially like a short, in which case the capacitor is shorting out this resistor R at AC signals, and we basically lose that resistor in terms of operating as a voltage divider. So that's why we say that is a low pass network. So let's analyze our loop gain. And so what we're thinking in terms of our loop gain, let me just sort of loosely draw a path here. So we're saying we have this input signal which we've included to help our analysis. So we have that coming in here, and then as we've already said, we have this non-inverting configuration. So based on our R1 and R2 value, we're going to amplify that and get some output value. So then of course we're going to have some feedback going on. So our feedback is going to be through this high pass and low pass network here. And so what we're going to see is that we have on this feedback part a voltage divider, where our input to the voltage divider is that output voltage V out, and then sort of the output of that voltage divider is our feedback voltage here, which is being added back into our input. So that's sort of the basic idea of our loop gain. We're sort of going from the input to the output and then back to the input. So let's come back and formalize that. So we want to find our loop gain, because again, remember all of our definitions for stability are based on our loop gain. So we can say our T of S is then equal to, so from our non-inverting amplifier, sort of our basic equations from previous classes, we know that the gain is going to be 1 plus R2 over R1, where R2 is that resistor that is feeding back to our inverting input terminal. And we have the second term, which is our feedback part, and so that's going to be ZP divided by ZP plus ZS, where the ZP and ZS are the impedances of our parallel network and our series network respectively. And so to be consistent with the notes, I don't know that I reference this later, but we can sort of think of these as two parts. So this is like our A, remember that's sort of like our forward gain, and then here we have this would be like our beta, this is our feedback transfer function. And so again, keep in mind we get this from our voltage divider, where we have our V out serves as the input to that voltage divider. And so to be consistent with the notes, I'm going to call this equation 1. So what we want to do then is we want to figure out expressions for the ZP and ZS to plug into there. So it's pretty straightforward to show that our ZP is R divided by 1 plus SRC, and our ZS is equal to 1 plus SCR divided by SC. And again, keep in mind our S is equal to J omega, so we can keep the S as we're doing these calculations in algebra, and then at the end we're going to plug back in our J omega to find actual frequency values. If you have any questions about finding the ZP or this ZS, definitely let me know, but I don't want to go through the details here. So now what we're going to do is we're going to take these expressions for ZP and ZS, and we're going to substitute them up here into this term representing our beta, our feedback transfer function. So let me just write what that looks like, and then we're going to skip a lot of the algebra, but it is shown in detail in the notes that are posted on Canvas. If you have any questions about that, let me know. But again, the main purpose of going through this is so you have a better understanding. I'm not necessarily looking for you to be able to do this algebra sort of off the top of your head on the fly in an exam situation. So there's our ZP equation in the numerator, and then in the denominator we have R divided by 1 plus SCR, so that's our ZP as well, and then we're adding that to our 1 plus SRC divided by SC, which was our ZS. So again, there's detailed notes posted on Canvas, but just doing some algebra, combining those terms in the denominator, canceling out some things, multiplying by some special forms of 1, and then gathering terms. Again, all of that's on Canvas. What we can find is that this loop gain, T of S, is equal to this quantity 1 plus R2 over R1 out front, and then that's being multiplied by 1 divided by 3 plus SRC plus 1 divided by SRC. And so to be consistent with the notes, I'm going to call this equation 2. Okay, so here is sort of the end result of our loop gain equation. So let's go back and remind ourselves of what we were looking for. We said initially we wanted to have this feedback network introduce a 0-degree phase shift. So let's come down here and see what that means in terms of this equation. So I'll just write this here. We want a 0-degree phase shift. So what that means in terms of this equation is that we want this. So let me move my 2 over here a little bit. So what that means here is that we want this to be equal to 1 angle 0 degrees. And so we can call this condition, so actually let me adjust this a little bit. Again, just to make things consistent with the notes, so if you're looking at that, you're not confused. So in the notes, I actually have this second equation here called 3. And then let me erase this from up here. Okay, so basically I've just, of course, copied that, and with that condition that we want our loop gain equal to 1 angle 0. So we know that then if this is going to be equal to 1 angle 0, and so actually let me adjust this. I've noticed I've actually come back, and in this equation we've substituted in for our j omega. So let me just do that real quick, and we're saying we're investigating our oscillation frequency omega naught. So let me substitute in these other two places as well. So our s's here are going to become j omega naught and j omega naught. Okay, so I think we're good now. So what we're saying is that we know that this t of j omega has to be real. So it must be real. And what that means is that the imaginary part of this equation 3 has to be 0. So imaginary part of our equation 3 must be 0. So similar sort of games that we were playing when we were looking at our phase shift oscillator. So what that means is we have this right here. These are our components that have j's, so that's going to be our imaginary part. We want that to be equal to 0. So we can say our j omega naught rc plus 1 over j omega naught rc is equal to 0. So remember, 1 over j is a negative j, so using that and then factoring out j, we have j times omega naught rc minus 1 over omega naught rc is equal to 0. And of course now we can get rid of that j, and solving for that gives us our oscillation frequency omega naught is equal to simply 1 over rc. And so to be consistent with the notes, let's call this equation 4. So now what we can do is we can take this equation 4 and we can plug it into 3. So if we take this oscillation frequency and we plug it in here and here, we can figure out the required ratio for our resistor R2 and R1. So plugging 3 into 4, or rather 4 into 3, what we get is our T of j omega is equal to, and so that's omega naught, is equal to 1 plus R2 over R1 times 1 over 3. Because as of course by design, all of this imaginary part here goes to 0, so we're just left with that 3. So we have 1/3. And that magnitude has to be equal to 1. So what that means then, if we solve for that, we have R2 over R1 equals 2. But we have to keep in mind that this is sort of our limit for the beginning of spontaneous oscillation. So this is our limit for beginning of oscillation. So in terms of design, if we want spontaneous oscillation, we then say that our R2 over R1 has to be greater than 2. So that covers our Wien bridge oscillator. So just a few other types that I want to mention that we're not going to cover in as much, well, we're not going to cover in any detail, but if you're curious, you can look into it more. If you ever find yourself working with oscillators, at least you'll be familiar with these names. So these are oscillators with transistors and LC feedback. Okay, so just to name some of these common basic oscillator structures, one is our Colpitts oscillator. And the second is our Hartley oscillator. And so the Hartley oscillator is actually just the dual of the Colpitts. The only difference is we swap our capacitors for inductors. So one of them has capacitors in a certain place and inductors in the other, and then when we go from one to the other, we basically just swap locations of those two. So these are sort of the dual of each other. So again, if you're curious and you want to look into more about how these operates, you can look on pages 1082 to 1083 in Niemann. And again, the main point here is just so you're at least familiar with these different types of oscillators, and ultimately, big picture, you know that, of course, there's more material out there than what we can cover for a single class.